when you work with mice, it's easy because you control everything. But with people, there's a lot more going on that affects health. So it's not just about internal locations within your body of molecules, it's also external exposures to all those molecules that are going to affect you.
If Laura-Isobel McCall's work had a motto, it could be location, location, location. Whether it's a disease inside your body or the molecules around your office, it's the where that's made her research so interesting. In this Season 2 episode of Bringing Chemistry to Life, we speak with another member of the Chemical and Engineering News' 2020 Talented 12 about their work and trends in their field. I'm your host, Dr. Paolo Braiuca from Thermo Fisher Scientific. We began by asking Dr. McCall about how she got to where she is today in her career.
I was very lucky in multiple ways. So I had a postdoc mentor who was very open-minded, gave me considerable freedom. So he hired me for a specific project, but he said, whatever else you do, you need to do that work, but with your extra time, you can do whatever you want. And so I was able to do that from his point of view, and then I secured my own funding, which again gave me freedom to pursue my own interests. So that's one part, because you need that kind of mentor who's going to let you do that. And then when the lab moved to UC San Diego, I met Peter Dorstein, who was very persuasive, saying that you have to do metabolomics. Small molecules are the answer to everything. I'd done some proteomics before, and I was leaning towards doing more of that. And he said, no, small molecules is the be all and end all. And so, I had the opportunity, I was in the right place. I had the opportunity to collaborate with his lab. And that's where I was able to learn the tools and the techniques. So he created the kind of environment where other researchers can come and learn from his group, use his instrument. And so that was the second piece. And then the third piece is that the University of Oklahoma, I think, was very open-minded because they took a chance on me because I didn't have necessarily the safest or most traditional background. And so especially Robert Chehevich here really advocated, I think, for taking a chance. And I think you need all those pieces to really be able to be this person at the intersection of multiple fields that doesn't necessarily fit in a nice square little box.
So if I get it right, your background is more on the biology and biochemistry studies, but you currently work in a chemistry and biochemistry department. So how did you get here?
I think the questions that we ask are biological, microbiological in nature, but the tools that we use are chemistry. I mean, our workhorse is our liquid chromatography mass spectrometry system. So we do a lot of analytical chemistry approaches to understand our biological systems. So I would say it's a true marriage of the two fields, with some computational aspects thrown into the mix to keep things interesting.
It is interesting. And if I think about some of the most exciting applications of chemistry, they typically all are at the interface with some other disciplines, very often biology, right? And very often it's very multidisciplinary. There's not only chemistry and biology, there's also something else in the mix. And it seems like in your research, there's a lot of that. Am I right?
Oh, yes, definitely. Because I think we start with biology, right? Where we get the samples, whether we're doing clinical samples, animal model samples. So it needs to understand the biology to help us design the studies properly. But then we extract metabolites, we perform chromatography, we perform mass spectrometry, we're looking at spectral data. So now it's transitioned to becoming analytical chemistry. And then once we have that data, it becomes a marriage of computational methods because we're dealing with huge amounts of data. But also you always need to go back to the raw spectral data to make sure that the quality is still good, that the computational predictions are correct. And then when you're taking all that knowledge, once you've verified that it's accurate, now you're trying to understand disease. So you're back again to biology and back and forth as you see something, check the chemistry of it, look at what you can learn about the disease over and over and over again. We work a lot with also people in, not just microbiology, infectious diseases, but also people in anthropology department. So that's much beyond my expertise, but at least being able to listen to what matters to them and then find common ground with our approach.
And if you look back, what were your challenges coming from your background and what were your advantages? actually, working in a sort of different field from where you were coming from.
Yeah, I think one advantage goes back to what we were saying about interdisciplinary collaboration, because just by virtue of my background and who I'm interacting with on a day-to-day basis, I'm forced into those conversations. And so you get regular practice at talking across different perspectives. The combination of my background and the technology and the approach has really led us to get brand new insights into diseases that would not have been possible, I think, without the marriage of those aspects. It's also really good, to be honest, to train students, because I can understand the challenges as we go along. Because whether they're from an analytical chemistry background and learning the biology of our diseases is challenging, or if they're biochemists who are scared of using the LCMS, or computational people, I can relate to all those challenges and all those aspects. So I think that's really helped me when I mentor students across different levels. I think probably the biggest challenge is, miscommunication, but also a fair amount of, I guess, imposter syndrome, for lack of a better word. Thinking, why did they pick me? What am I doing here?
How did you overcome this?
I don't think it's overcome. I think it's ongoing. But people, I think it's not just me, right? We all feel at a point in time. I think the scariest bit was when we just got the LCMS installed, and I was just standing in front of that instrument thinking, oh gosh, like, this is my instrument now. And we also had the first project that we ran on this instrument was a 680 sample project. So I guess I don't believe in starting small. But once we got through those 600 samples, it also really helped, I think.
Indeed. And that's the perfect segue to jumping into the science, right? So let's start looking a little bit of some of the works you do, that you've done. I think your work on Chagas disease is a perfect starting point for giving a simplification of your approach to science, how you marry the biology side of things with the chemical analysis and the computational analysis, for this multidisciplinary approach to diseases and metabolomics and all the rest you do.
Chagas disease is a really good example, I think, because it's probably the story that we have that's most advanced from beginning to potential translational applications.
Can we start from the problem of that study? So what answers were you after?
So a big question for me that's been underlying, I think, my entire research career is, why do things happen where they do? Chagas disease has very characteristic symptoms. Patients develop symptoms in the heart, in the esophagus, and in the large intestine. And so then by using chemical cartography, what we can do is make systematic maps of the chemical changes happening in each of those organs during the infection, and then long-term as the infection goes on, as parasite load becomes low, but disease worsens. And so by doing that, what it actually enabled us to see is that there's some spots where when the parasites go away, metabolism goes back to normal. Initially, after infection, there's a ton of parasites in the small intestine. Metabolism is heavily perturbed. But then the immune system kicks in, parasite levels go down, metabolism renormalizes. On the other hand, in the esophagus and the large intestine, so those are our sites of disease, parasite levels are going down, but metabolism becomes even more perturbed as time goes on. And so there's an inability of those organs to go back to normal as pathogen levels go down, and that can help explain why symptoms are happening here. So it's a chemical explanation for a clinical phenomenon. And then the next step that we've been doing from there is looking at which pathways specifically go back to normal or not, and using that to design new treatments for Chagas disease.
And you do this, but not looking at the microorganisms or the pathogen itself, but you look at all the hundreds or thousands of small molecules related to the metabolism of that specific organ at a certain moment in time.
So we do capture some parasite metabolites, but yes, the majority, especially as the pathogen load becomes really low, the majority of those metabolites are host-derived.
So let me understand what you actually do in practice. I assume you work with some animal models and you need to define some baseline. So do you take literally the organs out and slice them in very specific three-dimensional shapes and run an extraction and do, you mentioned LCMS or any other chemical analysis? Is that the way it works?
Absolutely. So we work a lot in animal models, although we're starting to transition, hopefully, in some autopsy samples as well as biofluids from patients. But in an animal model, we would collect the heart or the entire gastrointestinal tract, going all the way from esophagus to large intestine, and then we cut it systematically. And then we keep each piece, and then from each piece, we extract metabolites. For cutting the intestinal tract in 15 samples, that gives us 15 samples per mouse, 15 extracts per mouse. And then for each extract, we run liquid chromatography mass spectrometry. And so that gives us a very large number of data points per animal. And then we have replicate animals, different time points.
Are you looking for anything specific with your LCMS, or is it a completely untargeted analysis?
So we started primarily with untargeted analysis. Especially looking at Chagas disease, there's sadly very little research done on Chagas disease, almost none using LCMS. So we started with a true untargeted analysis. Now that we have specific pathways that we see being perturbed, we still have the samples, we still have the extracts in the freezer, so we can go back and do targeted analysis.
In my mind, this looks extremely complicated because I'm assuming that when you do an extraction for a piece of organ, you might have thousands of different chemicals in there. How do you recognize them all?
Annotating metabolites is, I think, the biggest challenge in metabolomics right now. Even with the top of the line best tools, we can put names to about 5 to 10% of them. We can extend that a bit, annotating at the family level for about 30% of the data, but there's still a huge amount that we can't annotate. So that's a big challenge. For sure, there's stuff that's very interesting, that's heavily perturbed by infection, and we have no idea what that metabolite is. We'll do some what I call guilt by association studies. So we'll see, okay, have any other data sets found that molecule? Because if you see it also being perturbed in, COVID-19 infection, and in hookworm infection, and in listeria infection, then maybe it's general infection related rather than specific to Chagas disease. But there's a fair amount of frustration in there. But I guess I'm a little used to frustration. I did some genomics on parasites. Leishmania parasites, about 70% of the genome is unannotated. So if you do transcriptomics, there's this gene that's heavily expressed, no annotation. And then I did drug development, high throughput screening, where our hit rate is less than 1%. So having 5-10% annotations actually is better success, in a sense, than a lot of things I'm used to.
We hope you're enjoying this episode of Bringing Chemistry to Life. Did you know you can register for a free Bringing Chemistry to Life t-shirt? Stay tuned at the end of the episode for information on how to request it, and also how to access interesting content recommendations from our guests. And now, back to our conversation. So, if you go back to the Chagas study, you mentioned that you found a somewhat surprising and very interesting lack of correlation between the level of the pathogens and the status of the metabolisms in that specific position, right in the organ. What kind of perspectives did this open? Is there a possibility for new therapies, or is there a new understanding of the disease that we didn't have before?
Before this work, no one knew why those were the target organs. And so that's, I think, game-changing in terms of our understanding of the disease. We already knew that there was a disconnect between parasite load and disease. But why those organs? That was our first insight into that question. And then it's important from a treatment point of view, I think. There's been kind of 3 phases, I think, in Chagas disease drug development. So initially, because they couldn't find parasites, they thought it was primarily autoimmune. Now that was disproven with the advent of PCR, really nice work in the late 90s, early 2000s. So then they focused on antiparasitic agents for treatment. But then around 2014, there were a couple clinical trials that showed that even if you kill off the parasites, if the patients have advanced disease it's not going to help them. And so I think we're now in the right stage to find new ways to treat Chagas disease, to understand that, yes, parasites are involved. Yes, we need to get rid of the parasites, but also host pathways are involved. And so my work helps us figure out which pathways specifically on the host really matter, to then be able to combine that with antiparasitic agents for better clinical care.
This is absolutely innovative because it somehow dissociates the therapy from the pathogen, and instead looking into the host metabolism and what can you do to reestablish, the normal equilibrium. I would say is that a right definition?
Yeah, because that's definitely what we're seeing in the esophagus and the large intestine. That parasite levels are very low and it's not going back to normal. It's becoming more and more perturbed as time goes on. And so we need a way to shift that balance. I definitely think we need antiparasitics, because I think without getting rid of the source of the problem, it's only going to be a short-term fix. But we also need ways to renormalize metabolism as we treat the disease.
Your approaches, particularly the use of 3D metabolomics, seems to be more general, right? Can we comment on a couple of other applications of your studies? I know you're looking into microbiome, for example. That's an interesting area. Can you discuss a bit more about that?
Yeah, I think microbiome is also a place where you need to be comfortable with the unknown still. There's been a monumental body of research, beautiful work being done on the microbiome, but causality linking specific pathways with microbiome and disease, I think that's still in its infancy, but that's the most exciting place, because that's, if you know causality, then you can build interventions and have an effect. And I think we've gotten pretty good, this is perhaps me speaking as an outsider to sequencing, to put names to organisms, right? To say we have these different organisms in this healthy person, we have this different microbiome composition in this sick person. But it's not enough from a mechanism point of view. And so the microbiome is very interesting from a chemical point of view, because they make a monumental diversity of molecules. And then on top of that, they can induce responses in the host that change the host metabolome, either directly through direct interactions or indirectly by reshaping the immune system or via all those molecules that the microbiome makes. And so between all those aspects, I think there's huge scope for better understanding.
It's incredibly fascinating. I've also seen that you use this concept not only for looking inside the host, but also for looking outside of it, because there is nothing that prevents you to do cartography on the environment around us, right? And try and understand the relationship between the chemistry of the environment, the things we see, breathe, and touch, and our own lives.
Oh, definitely. So we've done this on the entire first floor of a couple of different buildings. So looking at molecule traces on, couches and door handles and elevator buttons and floors and railings and water fountains. So it's, I think, really limited to people's curiosity and the kind of samples we can access. And that can give us huge insight into behavioral aspects, because I think when you work with mice, it's easy because you control everything. But with people, there's a lot more going on that affects health, and where we live, what we do every day is going to affect health. So it's not just about internal locations within your body of molecules, it's also external exposures to all those molecules that are going to affect you.
How did you come up with the idea, and why?
So that's something that Peter Dorstein's group was doing. They did a bunch of studies of the built environment when I was there. They did a water fountain in one of the research buildings, and they found traces of lab chemicals on those surfaces. And so that got me thinking about workplace exposures and how, we talk about chemical exposures in the workplace. A lot of people think about, like heavy industry, right? People who work in chemical plants, people who work in production. But even if you're working in a research lab, there's a lot of stuff in there that you really don't want to have on the cafeteria table. And so your exposures are very different if you're working in a building that has research labs or if you're working in an office tower.
What did you learn from the study?
We learned that you can classify a building's, surface metabolome depending on the function of the building. So there's a really clear separation between research buildings, teaching buildings, and office buildings. What we haven't done yet is deconvolute that from just, I guess, flow of people, because the teaching building that we studied, people are going in and out constantly. So is it just that there's more molecules because there's 700 people going through those doors at 9 a.m. every Monday morning? But they're very, very different.
This also led me to, to my fascinations for your commentary on physical anthropology. By the way, a very interesting journal for a chemist to publish on, right? Where you were discussing some ethical implications of metabolomics. It's extremely interesting and something probably very few people have thought about. Can you please introduce us to the ideas?
Yeah, I think some of it comes from our work on the built environment. So there's a reason why I'm not telling you where we sampled, what buildings we did, because that would be a nice story, right? But if you think about the kind of information we're capturing, we get information that people really don't want shared. There's a lot of worry about, date of birth, social security number, that kind of stuff. And that's extremely important from, an identity theft point of view. But really, if I told someone my social security number, they would know nothing at all about who I am. But then if I can list what they ate for breakfast, what kind of medication they took, do they wear sunscreen? Do they wear perfume? Now you're getting at information that people don't necessarily want told, especially when we're talking about prescription drug usage or illicit drug usage. And that we are able to capture with a lot of our LCMS approaches. So it's a lot of information that people really don't want disseminated. And so you need to be careful when you're handling that information, that you're not revealing whose house you just sampled. And there's also very big concerns from, I would say, a law enforcement point of view. There's this, I don't know if it's true or not, I haven't tested it, but there's this myth that almost half of US bills have cocaine on them. And some of it is, cocaine is sticky. Cocaine, it ionizes really well on our instruments. We can detect it pretty well. But if I find cocaine in your office, is it because you were using in your office? Or is it because the janitor was using and lifted things while they were cleaning? Or is it because it was the university bought the desk secondhand and 3 owners ago they were doing something? And so there's a lot of potential for misuse of that information. So that's also something we need to think about. The counter to that is, if you think about genetic information, that's completely fixed, right? So there's nothing you can do that can change it. So even though it's not very informative to other people, it's the barcode of your life. That's not going to change. Whereas if I find that you were eating citrus and you were taking blood pressure medication, maybe your blood pressure is better 6 months from now and you're no longer taking it. And, citrus fruit is no longer on sale at Walmart, so you've switched to eating apples. So that evolves as well. So there's dangers with all kinds of information, I would say, and we just need to keep those in mind.
Yeah, so genetics defines who I am. Metabolomics defines who I am and what I do. Is there any legal framework around that? Because that's a lot of information you can potentially get out of a person.
Not that I know of. And I think at the time that we wrote the perspective, a lot of the regulation around health information is focused on date of birth, social security, address. There's some regulation as well around use or misuse of genetic data, but very little around the metabolome. And there's some debate as to whether the metabolome could be squeezed into that genomic definition or not. But that's still to be determined.
So what is the promise here? What can we still do with chemical cartography and studying metabolomics on the basis of what you learned so far and what you have in mind for the next future and maybe even longer term? What is the horizon?
I think the promise is drugs that work better for people. So, because I think if you focus too much on clearing the pathogen, you're not really addressing what's actually causing the symptoms. Because there's a certain amount of, I guess, elasticity in our ability to live. Because we're pretty good at adapting to the pathogen presence. And sometimes some of those adaptations is what's actually causing the symptoms. And so I think it opens up a whole new way to think about drug development, to find better treatments that are able to compensate for the symptoms, improve how people feel. And so I think because it's underexplored, I think it has a lot of potential to find solutions for many current conditions.
This is brilliant, and it's super fascinating. I have enjoyed looking into your work because it's so different, it's for a chemist like me is blowing some fresh perspective on things. So now that you are still young but already an accomplished multidisciplinary scientist, right, with a very interesting personal and professional history, if you can stop and look back, what is a piece of advice you would pass on to a younger scientist just starting in their career?
I would say do what you love, because I think if you try to overthink career options and plans, I never saw myself doing an analytical chemistry research focus. One of the things that terrified me when I was doing organic chemistry in my undergrad was 3 lectures we had on mass spec. And looking at those spectra and trying to make sense of them was, I think I studied more for that part of the class than all my other classes combined. So I certainly never saw myself doing what I do, but just by doing things that interest me and being open-minded to what we could do, this is where I got. And I think this past year has shown us that we really can't plan for environmental catastrophes in a sense. But at least at every step of the way, I've always told myself, whatever happens, I'll have enjoyed what I was doing. I'll have made a difference. And so even if this doesn't work out, I'll still have spent another 5 years doing something I love. I'll still have spent another 10 years doing something I love. So just trying to live without regrets, in a sense, from both a personal and a professional point of view.
That was Dr. Laura-Isobel McCall, assistant professor at the University of Oklahoma and one of the Chemical and Engineering News's Talented 12. Thanks for joining us for this Season 2 episode of Bringing Chemistry to Life, and keep an ear out for more. If you enjoyed this conversation, you're sure to enjoy Dr. McCall's book, video, podcast, and other content recommendations. Visit thermofisher.com/bctl to access these recommendations and register for a free Bringing Chemistry to Life t-shirt. You can also find the URL in the episode notes on your app. Have a look. This episode was produced by Matt Ferris, Matthew Stock, and Emma Jean Weinstein.